Let's talk about ice. You've walked on it, you've slipped on it, maybe you've fallen flat on your back because of it. You've watched ice skaters glide across frozen ponds like they're defying friction itself. You've seen hockey players accelerate and stop on a dime, carving up the ice with their blades. So ice is slippery. Everyone knows that. It's one of those facts about the world that seems so obvious, so self-evident, that you probably never even questioned it. You just accepted it. Ice equals slippery. Water equals wet. Sky equals blue. These are the things we learn as children and carry with us forever. But here's my question for you. Why? Why is ice slippery? And I don't mean because it's smooth or because it's cold. I mean really, fundamentally, at the level of atoms and molecules and forces. Why does ice behave this way? What's actually happening when your foot touches that frozen surface and suddenly you're fighting gravity? Think about it. Can you explain it? Most people can't. And that's where things get interesting. Now, you might be thinking you already know the answer. Maybe you heard something in school. Maybe you read it somewhere. The most common explanation people give is this. Ice is slippery because the pressure from your foot melts the surface, creating a thin layer of water, and you're actually sliding on liquid water, not solid ice. That's the story. Pressure melting. Sounds reasonable, doesn't it? It even sounds scientific. There's pressure involved. There's a phase transition. There's a logical mechanism. It satisfies our need for cause and effect. But here's the problem. That explanation is almost completely wrong. Oh, it's not entirely wrong. Under very specific conditions, pressure melting does happen. But it can't possibly be the main reason ice is slippery. Why not? Let's think about it. To melt ice with pressure, you need enormous pressure. We're talking about pressures far greater than what your foot or an ice skate can generate. If pressure melting were the primary mechanism, then ice wouldn't be slippery at temperatures well below freezing. But it is. Go to Antarctica where it's negative 40 degrees. Ice is still slippery. The pressure from your body weight isn't melting anything at those temperatures. The numbers don't work. The physics doesn't support it. So if the standard explanation fails, what's really going on? Why is ice actually slippery? To answer that, we need to go deeper. We need to stop trusting what we've been told and start looking at what nature is actually doing. Before we can understand why ice is slippery, we need to understand what slippery actually means. What are we really asking? We're asking why there's so little friction between ice and other materials, between ice and your shoe, between ice and a steel blade. Friction is the resistance to sliding motion between two surfaces in contact. High friction means surfaces grip each other. Low friction means they slide easily. So when we ask why ice is slippery, we're asking why the friction between ice and other materials is so unusually low. Now, friction is complicated. It depends on the materials involved, the roughness of the surfaces, the forces pressing them together, and something else, something crucial. What's happening at the molecular level, right at the interface where the two materials touch? That's where the action is. That's where we need to look. Let's think about a normal solid surface, like wood or concrete. At the molecular level, it's rigid. The molecules are locked in place, vibrating a bit, sure, but not moving around freely. When you press another surface against it, the molecules at the interface interact. They create bonds, temporary attractions, mechanical interlocking between rough spots. All of this creates resistance to sliding. That's friction. But ice is different. Ice is water in its solid form, and water is a strange substance. It doesn't behave like most materials. Here's the key insight. The surface of ice is not like the interior of ice. In the bulk interior, water molecules are locked into a crystalline structure, a beautiful hexagonal lattice where each molecule is hydrogen bonded to its neighbors. It's rigid, it's organized. But at the surface, something remarkable happens. The molecules at the very surface don't have neighbors above them. They're exposed to air, to nothing. Their hydrogen bonds are incomplete. They're in a state of frustration, you might say. They can't complete their usual bonding pattern. And because of this, they behave differently. They're not quite solid. They're not quite liquid. They're in a peculiar intermediate state. This is the clue. This is where we need to focus our attention. The surface of ice is special, and that specialness is what makes ice slippery. So let's dig into what's happening at the surface of ice. In the interior of an ice crystal, every water molecule is hydrogen bonded to 4 neighbors in a tetrahedral arrangement. This creates a rigid, stable structure. But at the surface, molecules are missing neighbors on the outer side. They have unsatisfied bonds, dangling connections going nowhere. This creates what we call surface energy. The surface is in a higher energy state than the interior. Nature doesn't like high energy states. Systems always try to minimize their energy. So what does the ice surface do? It rearranges itself. The molecules at the surface become more mobile. They start to behave less like a solid and more like a liquid. Now, this isn't full melting. The temperature is still below the bulk freezing point of water. But the surface molecules, because they're in this special environment with incomplete bonding, have more freedom to move. They vibrate more. They rotate a bit. They slide past each other more easily. Scientists call this a quasi-liquid layer or a liquid-like layer. It's a thin film, just a few molecular layers thick, that exists on the surface of ice, even when the bulk temperature is well below 0 degrees Celsius. This phenomenon is called pre-melting or surface melting, but don't confuse it with pressure melting. This isn't caused by pressure from your foot. This is caused by the thermodynamics of the surface itself. It happens spontaneously. It's a property of ice, not a result of external force. The thickness of this quasi-liquid layer depends on temperature. The closer you get to 0 degrees Celsius, the thicker it becomes. At negative 10 degrees, it might be just a few nanometers thick, maybe 10 or 20 molecular layers. At negative 1 degree, it might be thicker, maybe 100 nanometers. But even at negative 30 or negative 40 degrees, there's still some molecular mobility at the surface. It never completely goes away until you reach extremely low temperatures. This is what makes ice fundamentally different from most other frozen materials. Most substances, when they freeze, have surfaces that are just as rigid as their interiors. But water, because of its unique hydrogen bonding structure, because of the way those bonds are directional and specific, creates this surface layer that's neither fully solid nor fully liquid. It's in between. And this in-between state is slippery. Why? Because when you slide something across this quasi-liquid layer, you're not sliding solid against solid. You're sliding solid against something that can flow, something that can deform and rearrange itself with very little resistance. The molecules in this layer act as a lubricant. They reduce the friction dramatically. This is the primary reason ice is slippery, not pressure melting, not smoothness, but this fundamental property of the ice surface itself. Now let's talk about what happens when you actually step on ice or skate across it. Does pressure play any role at all? Yes, but not in the way most people think. When you press on ice with your foot or a skate blade, you're concentrating force on a small area. This does generate significant pressure, and this pressure can have an effect, but it's subtle. The pressure doesn't just melt the ice outright. Instead, it enhances the quasi-liquid layer that's already there. Think of it this way. The ice surface already has this thin mobile layer because of surface thermodynamics. When you apply pressure, you add energy to the system. You stress the molecular structure. This makes it even easier for the surface molecules to break free from their crystalline positions and join the mobile layer. So the quasi-liquid layer gets slightly thicker under pressure. This is particularly important for ice skating. The blade of an ice skate is thin and sharp, concentrating your body weight onto a very small area. This creates enormous pressure per square inch. That pressure, combined with the friction and heat generated by motion, enhances the liquid-like layer right at the contact point. The skater is essentially gliding on an enhanced version of the quasi-liquid layer that already exists. But here's the critical point. Even without that pressure, even if you just placed a smooth object gently on ice without any significant force, it would still be slippery. Why? Because the quasi-liquid layer is already there. The pressure enhances it, yes, but it doesn't create it. This is why ice is slippery even when you're standing still, even when you're barely applying any pressure at all. It's why a gentle push can send you sliding across a frozen lake. The slipperiness is intrinsic to the ice surface. There's another factor we should consider: frictional heating. When two surfaces slide against each other, friction generates heat. Even though ice has low friction, it's not zero. So when you skate or slide across ice, a tiny amount of heat is produced right at the interface. This heat also contributes to enhancing the quasi-liquid layer. It's a feedback effect. The motion creates heat. The heat increases the liquid-like character of the surface, and that makes the motion even easier. So in practice, when you're skating or sliding on ice, you have all these effects working together. The intrinsic quasi-liquid layer from surface thermodynamics, the enhancement from pressure, and the enhancement from frictional heating. They all contribute. But the foundation, the reason ice is slippery in the first place, is that quasi-liquid layer. That's the key. Let's go even deeper. Why does water create this quasi-liquid surface layer in the first place? Why doesn't every frozen substance do this? The answer lies in the peculiar nature of water molecules and hydrogen bonding. A water molecule is polar. It has a positive end and a negative end. This polarity allows water molecules to form hydrogen bonds, which are relatively strong intermolecular attractions. In liquid water, these hydrogen bonds are constantly forming and breaking. It's a dynamic network. Molecules are constantly jostling around, making and breaking connections. When water freezes into ice, the hydrogen bonds lock into a specific crystalline pattern. Each molecule finds its optimal position and stays there, bonded to four neighbors. This creates a rigid structure. But hydrogen bonds are finicky, they're directional. They're not like the bonds inside a molecule, which are very strong. Hydrogen bonds are more like handshakes between molecules. They require specific geometry to work properly. At the surface of ice, the geometry is wrong. Molecules don't have their full complement of neighbors. They can't form all four hydrogen bonds. This makes the surface molecules frustrated and unstable. And here's where it gets interesting. For water, the energy cost of having an incomplete bonding network at the surface is high enough that the molecules would rather increase their mobility, would rather adopt a more liquid-like state than stay locked in a defective crystal structure. For most other materials, this isn't the case. For most frozen substances, the molecules at the surface just stay put in a rigid structure, even if it's not optimal. But water is different. The balance of energies is such that creating a mobile surface layer actually lowers the total energy of the system. It's thermodynamically favorable. This is why ice has a quasi-liquid surface and most other materials don't. Now, here's something truly mind-bending. This phenomenon isn't unique to ice. Other materials with directional bonding, like certain ceramics or semiconductor surfaces, can also exhibit surface pre-melting under the right conditions. But water is special because it happens at relatively high temperatures, temperatures we encounter in everyday life. Most other materials only show this effect at temperatures extremely close to their melting point, much closer than water. Ice shows significant surface mobility at temperatures 10, 20, even 30 degrees below its bulk melting point. This is unusual. This is what makes ice uniquely slippery among common materials. So the slipperiness of ice isn't just a quirky accident. It's a direct consequence of the molecular structure of water, the nature of hydrogen bonding, and the thermodynamics of surfaces. It's physics at the most fundamental level, determining a property you experience every winter. And that's beautiful. Now here's the part that should really freeze your brain. For over 100 years, scientists got this wrong. The pressure melting explanation was taught in textbooks, repeated in classrooms, accepted as fact. It sounded right, it seemed logical. But it was based on incomplete understanding and measurements that weren't precise enough to reveal what was really happening. It wasn't until the late 20th century, when scientists developed tools sensitive enough to study surfaces at the molecular level, that they actually figured out the truth. They used techniques like atomic force microscopy and X-ray diffraction to probe the surface of ice. And what they found surprised them. The quasi-liquid layer was there. It existed independently of pressure. It was a fundamental property of the ice surface itself. All those years, all those textbooks, all those confident explanations, wrong, or at least dramatically incomplete. This happens in science more often than you'd think. We create explanations that sound reasonable, that fit with our intuitions, and we accept them without rigorously testing them. And sometimes those explanations persist for decades or even centuries before someone bothers to look carefully enough to see the truth. The slipperiness of ice is a perfect example. It's a phenomenon everyone experiences. It's been known for thousands of years, and yet we only truly understood it in the last few decades. Think about that. Something so common, so familiar, so seemingly simple, and we got it wrong for generations. What else are we getting wrong right now? What other everyday phenomena do we think we understand but actually don't? That's the real question. So the next time you walk across a frozen sidewalk, or watch skaters gliding across a rink, or slip and catch yourself on an icy step, remember what's really happening. You're experiencing the consequences of quantum mechanics, of thermodynamics, of the peculiar structure of water molecules and the incomplete hydrogen bonding at the ice surface. You're interacting with a quasi-liquid layer just a few nanometers thick that exists because nature is always trying to minimize energy. That's what makes ice slippery, not pressure, not magic, but the beautiful, intricate physics of surfaces and molecules. And here's the deeper lesson. The world is far stranger and more wonderful than our casual explanations suggest. Every ordinary phenomenon, every everyday experience is the surface of something profound. If you dig deep enough, if you ask why enough times, if you refuse to accept the easy answer, you'll find layer after layer of astonishing complexity. That's what physics is really about. Not memorizing facts, but peeling back the layers of reality and discovering how things actually work. And that journey never ends. There's always another question, always another why.